Okay, so the title of my talk are What are PFAS and Why Bother? I'm a professor at Stockholm University in Sweden at the Department of Environmental Science. Okay, so what are PFAS? Well, PFAS, I guess most of you know, stands for per and polyfluoroalkyl substances. They are synthetic organic substances. That means they have no natural sources. They are man-made substances and would not be in the environment if they were not put there by us. There hasn't been a definition of PFAS from the beginning when we started research, but in 2011, the first definition of PFAS came. And last year, there was a completely new definition of PFAS introduced by the OECD. And I'm not going to read this out, but basically it means any organic substance is a PFAS if it contains either a CF2 unit or a CF3 unit somewhere in its chemical structure. With such a broad definition, this means that it captures many thousands of substances. And some of you may have heard of some of these lists of PFAS, and there are various numbers like 4,730 by the OECD, and the US EPA have a list of 9,252. Actually, neither of these lists have used the OECD definition, which is much broader. And so we don't actually know quite how many PFAS there are in use. But you can imagine that when you have such a broad definition of what PFAS are, that it means that they're a very structurally diverse group of substances. And that means also that they have very diverse properties. So they are polymers and non-polymers. So that's very large molecules and very small molecules. And they can be neutrally charged or they can be ionic. They can be solids or liquids or gases. They can be reactive or inert. They can be soluble and insoluble, volatile and involatile, mobile and immobile, bioaccumulative and non-bioaccumulative, highly toxic and relatively non-toxic. So you basically can get the picture. They capture kind of the whole spectrum of properties. But despite this diversity, because they all contain these fully fluorinated carbon chains, they're all highly persistent in the environment. More about that later. In fact, we don't know the environmental behavior and toxicities of most of the substances in this class. We've spent some work trying to work out the PFAS universe and dividing it up into various groups. And we understand it quite well. You don't have to understand it, but we try to divide them up into all of the different subgroups of PFAS. And you start by dividing them into non-polymers and polymers, and then under that you have all of the various chemical groups under that. Today, we're mostly going to be talking about polymers. And I'll discuss that a little bit more later. So why do we use PFAS in society? Well, they've been developed already from the beginning of the chemical industry in the 1930s. And some of the well-known PFAS were started to be manufactured, like PFOS and perfluoride already in the 1950s. So we've been using them for a long time, and this is because they have very useful properties. They're highly thermally and chemically stable due to the strength of the carbon-fluorine bond. The carbon-fluorine bond also provides both water hating and fat or oil hating, which is a unique property actually of these fully fluorinated carbon chains. So they're very useful as fluorosurfactants. They can lower the surface tension of water to much lower than hydrocarbon surfactants can. And they're also very useful in surface protection, like in non-stick coatings, because they have very low surface energies. So how widely are they used? Well, we conducted a survey of the uses of PFAS in 2020. We identified over 200 uses of PFAS for 1,400 individual substances. And you can see on this, the light blue bars are polymers. So polymers are actually used in higher volumes than the non-polymeric, the smaller molecules, the more famous molecules like PFOS and PFOA. And you can see that one of the biggest uses is in coatings, which we're going to talk about today. But there are many unusual uses that we also discovered, like in guitar strings and ammunition and climbing ropes and so on. So why bother about PFAS? Well, most of the research and concern regarding PFAS is based on these two
subgroups of PFAS, and these are the perfluoroalkyl carboxylic acids, which the most famous member of that group is PFOA, perfluorooctanoic acid, and also the perfluoroalkane sulfonic acids, which the most famous member of that group is PFOS, perfluorooctane sulfonate. And almost all of the research, even to this day, has been conducted on these two classes. So they come in a whole group with different chain lengths, from just one fully fluorinated carbon all the way up to 20 or more fully fluorinated carbons. So let's go in. What are the problematic properties? Well, I mentioned already that they are extremely persistent. And just to put that in perspective, compared to all of the other substances that we have studied in environmental chemistry over the last few decades, these are by far the most persistent substances. And you can see that we don't actually know how persistent they are because no one has been able to observe any environmental degradation or mineralization of these substances. So they could be over 30 years, could be over 100 years, and they've got the label as being forever chemicals because of this reason. They are, and because of this persistence, they are now everywhere in the environment and they will never go away. Also, the next problematic property is their bioaccumulation potential. So already early in the early 2000s, when we first started to research these substances, we started to discover that these substances were everywhere in wildlife around the world. So this is the case for PFOS. You find very high concentrations in these organisms relative to the concentrations in the environment they reside in, which is the definition of bioaccumulation. But not all PFAS are bioaccumulative. So, you know, we often think about these problematic properties and label all PFAS as having them. But if you just look at the perfluoroalkyl acids, in this case, the perfluoroalkyl carboxylic acids, you can see that some are bioaccumulative, the longer chain ones with longer fluorinated carbon chains, but those with shorter fully fluorinated carbon chains are not bioaccumulative. So they also bioaccumulate in us. So everyone in the world basically has these chemicals in their blood, which is also one of the big concerns. But again, not all of these PFAS are in your blood, but some of these well-known ones like PFOA and PFOS, you'll find everywhere in the general population. And if you go closer to point sources, you'll find concentrations in people's blood which are hundreds and thousands of times even higher than in the general population. And yeah, okay, they're everywhere. They're in, you know, they're in wildlife and they're in humans, but you know, so what? Maybe you still wonder why bother. But you may have seen this movie, Dark Waters, and as a result of the lawyer who worked in that, they managed to take a huge number of blood samples in this region, and were able to conduct very extensive epidemiological studies and link the exposure of the people in this region near a fluoropolymer manufacturing plant, actually, to 6 different diseases, and this was linked to the exposure to PFOA. So this, of course, has ended up in a big lawsuit, and lots of money had to be paid out by the chemical manufacturer, in this case, Chemours, used to be called DuPont. But we know that from laboratory studies and lots of other epidemiological evidence that for these well-studied PFAS, that there is good evidence for toxic effects. And when you see the same effects in both lab studies and in the general population, that is definitely a reason for concern. But again, I should say that most of this research has been conducted on a few PFAS. And so we know the toxicity of PFAS and PFOA, which have been listed on the Stockholm Convention, but we don't know the toxicities of most of the substances in this class. So that brings us to the question, are all PFAS of concern? Should we bother about all of them? Well, as I said earlier, all PFAS are highly persistent. This fully fluorinated carbon chain is basically non-degradable in the environment. So under the definition of PFAS, some PFAS will, I also said that some PFAS were reactive, and that's true as well. So some PFAS will degrade, but they will always ultimately degrade into terminal transformation products. So under the
European Union REACH legislation, this means that all PFAS are persistent substances because they either degrade themselves or degrade into very stable transformation products. But not all PFAS will be bioaccumulative and toxic, but they will all be extremely persistent. So should we be concerned about chemicals which are highly persistent, just if that's the only property of concern? Well, continual release of these highly persistent chemicals will result in increasing levels, and toxicity is all about thresholds. When you release something continuously, which is highly persistent, the levels will increase. And so ultimately you're asking for trouble, because if you do eventually find an effect, you cannot take the chemical away from the environment. You still have, it's still going to be there. So this, we have written a couple of papers and said that persistence in itself is something of high concern. So, and this is also the same argument that's been used for microplastics, that persistence of these substances is concern in itself. So that's the only way you can group all PFAS. And this is also from the reason why over 200 scientists signed this statement in 2015 called the Madrid Statement. And they suggested that production and use of all PFAS should be limited based on this high persistence, and also the fact that we don't know anything about most of the substances in this class. And this has also led to the restriction proposal in the EU, which we'll hear about in the next presentation. And when you lump PFAS all together, you're then concerned maybe about whether you have fluorine in your products. And this has led to the rise in popularity of total fluorine methods. Rather than individually analyzing individual PFAS, you then look for just the organofluorine in a product or in the environment. So we're going to talk today about fluoropolymers. So I'm going to focus on one particular part of the PFAS universe. So here on the right-hand side, we have all of the polymers that belong to PFAS, and in the subset of polymers, we have fluoropolymers, things like PTFE, which have fluorine in the backbone of the polymer. So that's what we're going to talk about a little bit more now, in more detail now. So fluoropolymers are, in themselves, there are many different kinds of fluoropolymers, but they are dominated by the polytetrafluoroethylene, or PTFE, and that's used in a lot of different consumer products. And you could see also that the production volume of fluoropolymers has been increasing year on year up until the current day. And the chemical industry would like this to continue, as you can see in this paper, the promising future of fluoropolymers, and that they would like to find more and more uses of these substances and increase the volume of the uses. We're talking today about fluoropolymers and PTFE in particular, because it's used in non-stick cookware. But is it a problem? And the chemical industry have invested quite some effort into saying it's not a problem. And this is paper trying to say that PTFE and other fluoropolymers are what's called polymers of low concern. And there's an OECD criteria for this, so-called polymers of low concern. And they've looked at various criteria to try and suggest that PTFE in non-stick cookware meets these criteria of polymers of low concern. So they say that PTFE is inert and not bioavailable because it's a big molecule. They say that they've done a lot of work on removing the residuals in the products so that there are no toxic impurities in the PTFE coatings. They are very low, it's true, the residuals these days, because they now these days invest a lot of effort into removing the residuals of, which used to be things like PFOA, and these days other chemicals like Gen X, which would be in the products, but now they spend a lot of effort removing these during the manufacturing process. There are issues during the use phase if you use your pan above the recommended temperature range. So if you heat up your pan above 250 degrees, which can easily happen in the kitchen, you can produce some toxic chemicals, toxic gases above the pan. But according to risk assessments that have been done, the levels are very low, and at least for humans, and should be not concerned. So according to this paper, PTFE do meet these criteria of polymers of low concern, these OECD criteria. And so, but does that mean that they are really of low concern? So we were kind of a bit sort of surprised by this paper, because I found it a little bit insulting considering all of the problems that have been associated with fluoropolymers in the past. And it focuses only on the use phase. And in the case of fluoropolymers, life cycle considerations are critically important. As you remember earlier, most of the problems with fluoropolymers is a result of the manufacturing of the fluoropolymers. So all of the chemicals are released, such as PFOA and GenX, around the manufacturing plants, which was the subject of the Dark Waters movie. And then also at the end of life, how do you dispose of these substances in a responsible way? So this polymer of low concern criteria completely misses the life cycle considerations. So we know that during the manufacture of fluoropolymers, we use these processing aids. Historically, we used PFOA as a processing aid. So we had a huge release in the US, Europe, and Japan of PFOA from fluoropolymer manufacturing during the manufacture of fine powder PTFE, which is used for making the non-stick surfaces. And this is basically almost all the PFOA that's in the global environment as a result of this historical manufacture of fluoropolymers. And still today, PFOA is used in large quantities in China for making PTFE and other fluoropolymers. Manufacturers in US, Europe, and Japan have now switched to alternatives, but these alternatives are also being proved to be problematic. They're also PFAS, and they're also extremely persistent and present in the environment around, in high concentrations around these manufacturing plants. Here's a couple of these alternatives at the bottom, the one often known as GenX, and which is the alternative by Chemours, and the one on the right is the alternative developed by 3M. So each manufacturer has actually developed their own alternative for PFOA. And this has caused, fluoropolymers have been in the media because of all the wrong reasons, because they have contaminated the environment around fluoropolymer manufacturing plants, both in Europe. The top left there you see Dordrecht, which is a Chemours site, which is now releasing GenX. And then you'll see, Dark Waters, which is all about the PFOA that's released in the US, and other movies and press releases and so on about the problems with fluoropolymer manufacturing. So during the manufacturing, the manufacturers release these processing aids like PFOA, GenX, and so on, but they also release a whole range of other things, such as volatile fluorinated byproducts with global warming potential, and also multiple other PFAS. And so some of us academics have been looking around these fluoropolymer manufacturing sites and finding all sorts of weird structures in the environment there. So Chemours themselves have listed 250 novel PFAS that are emitted from their plant in North Carolina. And the US EPA have identified multiple PFAS in all the soils around the fluoropolymer manufacturing site. So this is a huge pollution problem and really an unknown problem in terms of what the effects would be on the people living around these plants. And then the other part of the life cycle is what you do at the end of life. Fluoropolymers they're not recycled in any significant quantities. The use of them results in the release of micro and nanoplastics. We find PTFE in the global environment, in Mediterranean fish and Arctic sediments. And how do we safely dispose of them? Maybe we have to incinerate at very high temperatures to destroy the fluoropolymers, and it's a bit uncertain whether this is safe and whether formation of fluorinated organic byproducts occurs. And this is a subject of ongoing research. The only research that's really been done to date has been done by industry, and they of course suggest that there's no problem, but we need more independent research to try and understand whether incineration of these substances is a problem. And when we think of PTFE coatings, we often think of our own usage in our kitchens, but remember that they are also used commercially, for example, in commercial bakeries. And in commercial bakeries, PTFE lines these baking trays and is then removed every 12 to 24 months and recoated. And the way it's removed is usually by either by burning off at quite low temperatures compared to what's safe for removing PFAS, and also either by water blasting, where the chemical is largely just released into the environment. So this results in largely unknown emissions of PFAS into the environment as well. So what are the solutions? Well, the solutions, of course, is maybe to stop using PTFE and non-stick cookware. There are alternatives, and some product manufacturers have switched to these alternatives. These include ceramic non-stick, cast iron, enameled cast iron, carbon steel, stainless steel, etc. Of course, there can be problems with these alternatives, and we shouldn't blindly switch to alternatives without evaluating them and doing life cycle assessments on them as well to understand we're not making a new problem. Another alternative is because a lot of manufacturers will say we need PTFE. It depends. There's quite a lot of differences of opinion in industry. Could we manufacture PTFE more responsibly? And yes, we could. We could stop using non-fluorinated processing aids. And in fact, there are patents for non-fluorinated processing aids, but there has been a reluctance in the industry to introduce this. It takes a lot of R&D, and only some manufacturers have introduced these non-fluorinated processing aids, while others have not. What about recycling and safe disposal? Well, that could also be improved. So we could use PTFE more responsibly than we do today. So this is a potential parallel solution. But it's unlikely, that PTFE would be considered, in its use in non-stick cookware would be considered an essential use of PFAS. So you could say that it could easily be phased out because it's not essential for health and safety, and there are also alternatives available for this use. That's really all I have to share today, and hopefully it was a useful introduction to this webinar. So thank you.